And when you read a problem, you might actually not know exactly where to begin. But the key part is understanding how to get what is called the effective mass, or what is called the moment of inertia here. Before we do that though, because of this term, the Ri, that is the distance from the pivot point. And if it's freely rotating, the pivot point is what is called the center of mass. So before we do anything, we need to understand what geometry we're actually dealing with, and then we can calculate the effective mass. And so what we went over last time was just an example of getting the moment of inertia of an object or a large object which has three smaller objects as its components. And we did calculate the moment of inertia for this specific object, and that was here. However, for regular geometries, such as an example like a rod, there is a table that provides for you what the moment of inertia is. And so you just look it up on the table, and it gives you a relationship, or is equal to some function of your mass as well as the size. So you do need to do a little bit of a legwork before you get this moment of inertia. So if you have a common geometry, you look it up in a table. If you have, let's say, this widget looking thing, then you would actually have to use this expression to compute the moment of inertia. Now, with this in mind, let's do a quick example. Let's do a qualitative analysis. So this would be quantitatively extracting the moment of inertia, but of course it is important and of great value to be able to do things qualitatively or conceptually as well. Let's say two identical rods are joined to make a T. So let's say the first one, A, A is actually like this. So it's joined to make a T, and it's going to be rotating about that axis point. Let's say B, we have the same T, except it's rotating around here. For C, we once again have that same T, and the only thing changes, this time it's rotating around that. And lastly, in part D, we have that same T, and we're rotating around this. So the dot is the axis of rotation. Now what we're tasked with is ranking in terms or in order of the moment of inertia I. Rank in order of I. So how can we do this? We can do this by looking at what this equation is telling us. What this tells us, remember this R is the distance from the axis of rotation. So this equation tells us that the more the mass is focused away from the axis of rotation, the larger the moment of inertia. Or the closer the mass is to the axis of rotation, the smaller the moment of inertia. that is the way to understand this expression here. So the further the masses spread out away from the axis of rotation, the larger the moment of inertia. The closer it is to the axis of rotation, the smaller the moment of inertia. So with that in mind, with that conceptualization, we want to rank in terms of increasing moment of inertia. Any guesses as to which one will have the highest I? Highest I. In which scenario is the mass most furthest away from the axis? Yeah.
Would be A.
Would it be A? Why do you say A?
Because the largest point is farthest away from the axis of rotation.
What do you mean largest point? What is
So I mean, the most weight is the farthest away.
Okay,
from the
yes. So here in A, the entirety of one rod is the full rod length away. In no other scenario is the entire mass of a rod the full rod length away. So if you look here, one full rod is right at the axis. Another one here, it's at the axis. Here, there is, the entire rod is half of a length of a rod away. And so IA is definitely the largest, that is correct. So the moment of inertia here would be the largest. Which one would be the smallest? Doing the, yeah, say it.
C.
C or B?
C.
Okay. Who agrees? Raise your hand. Okay, but let's make a comparison out of these two. So C is correct, but in both scenarios we have one full rod right at the axis. One full rod right at the axis. So that's not the distinguishing factor. What is the distinguishing factor is comparing the second rod, this guy, to this guy. In this case, we have half of the rod ends half the length of a distance away. That would be equivalent to this guy right here. Now, with the remaining, this one versus this one, which one is further away? This one is further away, so for sure, IC would be the smallest. And then you can compare B and D, and you will see B, one entire rod, is at the axis, whereas for D, that's not the case. So we can argue D is also greater than B, and this will be the correct ranking. So this was the short discussion on the center of mass as well as the effective mass called the moment of inertia. So this would be the analysis that you have to do pretty much before the problem even begins, and that's where the difficulty lies. Now for rotation, that's not the only thing that's important, because next we can move on to, well, what causes rotation? What causes rotation? At the fundamental level, it is still this concept of force. However, this force results in what is called the torque, or the moment, and it is this torque that leads to rotation. But to understand how the force ultimately goes to rotation, or meaning to better understand torque, let's do a thought experiment. Consider a door. Okay, who's used a door before? Okay, so let's say we have a door. And so this is, we're going to be doing some thought experiments, so try to visualize this along with me. This is going to serve as our hinge. And so as our base case scenario, let's say at the very tip of this door, we apply a force, and we will call this F1. And so our base case, we're going to observe that F1 opens door, let's say at a angular acceleration of alpha 1. Right, if you press on here, this is a hinge, the door is going to pop right open. Alright. But instead of applying a force this way, let's say we apply that same magnitude, except we apply it in this direction. And we'll call this F2. What's going to happen when we apply F2? Right, nothing. F2 does not open the door. But what changed between F1 and F2? We applied the same magnitude of force, and we applied it at the same distance away from that hinge. But what changed? The what?
The direction.
The direction. So we'll say theta changes the torque. The force, well, at least the magnitude was the same. But in terms of how the force gets applied to the torque, we see that there is a theta dependence. Next, let's say we apply that same magnitude of force, and then we apply it right here, and we'll call this F3. What will happen this time? Yeah, Matt.
It'll open, but it'll open a lot slower.
It'll open slower. So F3 opens door at rate alpha, which is much less than our base case alpha 1. So what does this tell us here? Compared to our base case, the magnitude of the force was the same. The angle was the same, but what changed?
Distance.
From,
The hinge.
yeah. So we see that distance changes torque. Yeah.
Sorry, could you repeat really quick for the alpha and alpha? So what does that part mean again? Where it's
This is the how fast it's accelerating.
oh, okay.
It's opening, if you apply it here, it opens much slower than this one.
Okay.
So the angular acceleration is much less than the base case here.
But why is it says alpha and alpha, what does that part mean?
Alpha is less than alpha 1.
Oh, okay.
This alpha is less than alpha 1.
Thank you.
We'll say this, alpha 3 is less than alpha 1. And lastly, let's say at this same point, instead of using the same force, let's say we apply half the force. Then what's going to happen? What's going to happen?
Open the door slower.
Yeah, F4 opens door at rate alpha 4 is less than alpha 1. Now here, the only thing that changed, well, it's because I can't draw the vector right on top of each other. The only thing that changed is the magnitude of the force. So mag of F changes torque. And all of this is encapsulated in a single equation where torque is defined as the R times the cross product of F. R cross F. because this cross product provides for us the magnitude is equal to RF sine of theta. R is simply the distance that the force is being applied, and so that is right here. Distance changes torque, that is this R right here. We also saw that theta changes the torque, that is sine of theta, as well as the magnitude of F changes the torque, and that is this F here. And so this is how torque and forces are related. Sorry, this is the magnitude What about the direction? How do you get the direction of the torque? Notice that torque is a vector. How do you get the direction? So here, what is the direction of the torque on the door? Who remembers how to do direction? Yeah. Shina, don't be shy. What is it?
Was it good?
Yeah, throw out your gang signs, right? Right. We need to use the right hand rule. That's how you get the direction of the torque. So let's focus on force 1. Okay. How we would do this, the R is the direction from the pivot to where the force is being applied. So our R would be this direction. This would be our R. So take out your right hand, it would be R. So we point it straight that way. All right, that's our index finger goes that direction. The middle finger goes in the direction of F. All right, remember not to offend anybody. So it's R cross F, like that. And the direction of our thumb, it's out. And so the torque direction is actually that. That would be tau 1. It's coming out of the page. What this means is a counterclockwise rotation. So this being the torque means counterclockwise rotation. Those are hand in hand. So if it's going counterclockwise, the direction is out of the page. So that is how we would do it. And so here, theta, let's be a little bit more specific. It's angle between R and F. And so let's look at a quick example here. Let's say a 20 centimeter long wrench is used to turn a nut. Let's say the wrench is tilted at 30 degrees above horizontal. Let's say Bob pulls down at 100 newtons. The question is, what is the torque Bob applies? I don't know who was first.
That's you first.
Yeah.
Does that say a 20 centimeter long rod?
Wrench, yes. Okay, wrench. Alright, so the scenario we have a nut like this. Here's our wrench. And it is tilted at 30 degrees. on the horizontal. And Bob, let's say, grabs the end and then pulls it straight down at 100 newtons. And let's say this distance is 20 centimeters. And we want to know what the torque is. Torque, at least the magnitude, is RF times sine of theta. What is R in this scenario? It is the distance from the center of the or the pivot point to where the force is being applied. How far is it? So it would be, in this case, here all the way to here, which is what length? 20 centimeters, but we wanted an SI, so it'll be 0.20 meters. F is the magnitude of the force being applied. In this case, Bob is applying 100 newtons of force. Times the sine of what is the angle, what is theta? 30 degrees? Who agrees? Who disagrees? What?
So they need to be radians.
Well, if it's a sine, then it can be either one.
Oh.
Just your calculator needs to be in the correct format. It is not 30 degrees.
Would be 60.
60 degrees, who agrees? Where'd you get 60?
Well, you would need to do cos 30 degrees, which is the same as sine 60.
Wait, why would you need to do cosine of 30 degrees? Because this is sine of theta.
Well, because you're looking for the looking for the component of the force that's kind of acting 90 degrees to the direction of R.
90
Are you
degrees.
not?
No. Is it 90 degrees
So
of
you
R?
want the components of that force that's acting. Yeah, so that's like what you're trying to find.
Okay, that's true. Well, okay, it is, well, 30 is closer to 60. I'll say that much. But ultimately, this is our R vector, and this is our F vector. When we actually compare the two, for the proper vector comparison, this is going to be our R, and that is going to be theta, which is equal to 30 degrees. Our F vector, we have to have originating as the same origin. So what is the angle between R and F now? Well, this is 90 degrees. Yeah, so this entire angle is theta is actually 120 degrees. That is actually the angle in between, which will get you negative 17 Newton meters. Yeah, that's still. What does this negative mean? Any ideas? Yeah.
This is because it's inside down.
Well, forces are being applied down, that's true, but this is torque.
Going clockwise.
Clockwise is correct. If it's positive, it's trying to rotate it this way. but negative means it's trying to go clockwise. So convention, positive is counterclockwise, negative is clockwise. And so that's why the sine of 120 was important. Technically, sine of 30 will give you the same value, but it won't give you this negative, the negative number. So sine of 120 is what gives it negative. Of course, you could have just understood, well, this force is going to make it rotate in the clockwise direction and just made it negative afterwards. That's completely fine too. But positive is counterclockwise, negative is clockwise. So that's how to calculate the torque. But why do we even care about the torque? Just like how Newton's second law provides a cause for a motion, we have Newton's second law for rotation, which gives us the relationship between the torque and the rotational motion. So here, this is how we get force is equal to mass times acceleration. This was Newton's second law for translational motion. But when this is applied to rotation, just by using that table that I mentioned before, whenever you see a force, it becomes a torque. And when you see a mass, it turns into the moment of inertia I. And when you see acceleration, it turns into alpha. This is Newton's second law for rotational motion, where tau net is simply the sum of all the different contributions which we can write it as the following. So this is why we care about the torque. We just talked about how much torque Bob can apply. Yeah, but how does that translate to how fast the wrench actually moves? We would have to use this expression. We would have to understand what the moment of inertia is, and then we could compute what the angular acceleration will be. Now, just like in translational motion, we had a condition for mechanical equilibrium. So we have an equilibrium condition for rotation. And in translational motion, the only thing that we cared about was this, that the net force on our system was equal to 0. However, when we apply this to rotational motion, what do you guys think the equilibrium condition will be? When will it be in rotational equilibrium? When?
Net force of the torque is 0?
Well, not net force of the torque, just net torque.
So net torque, well,
Net torque, yes. Tau net is going to be equal to 0. Now, in actuality, it's not just this, the net torque has to equal 0, it's both of these conditions must be met for rotational motion. Is that F net is equal to 0 and the net torque is equal to 0. But the steps for doing this properly is the following. We must establish, or not establish, we'll say identify, actually before identify, we must correctly identify. So we must correctly identify the pivot point. So this is the first step. You have to correctly identify the pivot point, and only then can you actually apply the equilibrium conditions. So then can apply F net is equal to 0 and tau net is equal to 0. And so let's do an example with this. And this is considered to be a classic physics problem. And it's the hanging chandeliers. The chandelier problem. So let's say you have a stable chandelier. And so we have something hanging from the ceiling. And let's say the chandelier can be modeled as one object hanging here. Let's say it is 1 meter away. So this chandelier is gigantic. Let's say there's a object hanging here, and let's say this is 2 meters away. And let's say there's a third object here when this is 3 meters away. So we'll call this X. We'll call this, let's say this is 1 kilogram and this is 2 kilograms. And so we'll label the objects as the following: 1, 2, and 3. And the question that we want to answer is, what is X? So what mass is here at object number 1 so that it is stable with these two other masses hanging over here? We also want to know what is the total tension, the tension on this rope here. So we have these two questions. So the first thing that we have to do is understand or identify where the chandelier will be pivoting. Where will it be pivoting? Where would the pivot point be?
Wherever the rope attaches to the chandelier.
It will be right here. That would be our pivot point. So establish the pivot point is at the junction. So then and only then can we actually compute the torque. We have at this pivot point, the net torque is equal to 0. So tau net is equal to 0. Now, one thing to note. So if we look here, from our pivot point, this is our R, and our force of gravity is down, it's a chandelier, they're all the forces of gravity. This would be force of gravity coming from 1. What is the angle between these two forces?
90 degrees.
90 degrees is correct. And so remember, our torque expression is RF sine of theta. If our angle is 90 degrees, we want to know, or who remembers what sine of 90 degrees is?
Just 1.
Yeah, it is simply 1. Meaning, in all of our chandeliers here, they all have 90 degrees, meaning all of the torques are simply the distance times a force, because sine of 90 is just 1. Right? The angle dependence goes away. So here, the net torque that we have is simply, we have three contributions: torque 1, torque 2, and torque 3. So we have torque 1 plus torque 2 plus torque 3. However, there is a slight issue. Not all of these are trying to get it to rotate in the same direction. Remember, positive is counterclockwise, negative is clockwise. Which ones are trying to rotate about the junction? Counterclockwise.
Object one.
This way. Huh?
Object one.
Yeah, only object 1. Object 1 hanging down is trying to rotate this entire platform right this way. So this tau 1 is given a positive value. What about objects 2 and 3? They're trying to make it go clockwise, so these are given negative values. So this torque has to do with rotational motion. Clockwise is positive, counterclockwise is negative. It is no longer simply up or down or left or right. It is clockwise versus counterclockwise. So again, if it's counterclockwise, it's positive. That's why object 1 is trying to rotate it counterclockwise. Objects 2 and 3, they're trying to rotate it clockwise, so they're negative. And our equilibrium condition tells us that the net torque has to equal 0. So what we get is R1F1 minus R2F2 minus R3F3 has to equal 0. Or R1M1G minus R2M2G minus R3 M3G has to equal 0. Every single term has a G, so we can get rid of divide out the G for free. Alright, sorry, actually it's not. It's R1X, right? So our X then is equal to R2M2 plus R3M3 over R1. What is R2? R2 is 2 meters times mass of object 2 is 1 kilogram. What is R3? 3 meters is incorrect. Yes, it is 5, and this is very, very important. We are looking from this distance to that distance, which is 5 meters. So it's not this distance here, it has to be the distance from the pivot point. And so it is 5 meters times 2 kilograms divided by, what is R1? It would be simply 1 meter. And so if you do all of this, you'll get a value of 12 kilograms. So for this chandelier to be in equilibrium, you would need 12 kilograms hanging right here, and then you'll have the equilibrium condition met. Secondly, we want to know what the total tension is on this primary rope here. For this, we're going to be using the net force is equal to 0 equilibrium condition. And we're going to be doing it at the junction. So if we look at the junction here, so this entire platform can be thought of as a single point right here as a junction. And everything that's hanging off can essentially be understood as hanging off from the junction itself. So when we apply the free body diagram, you would have the tension, the total tension up, and you would have 3 different forces acting straight down. So force of gravity 1, force of gravity 2, and force of gravity 3. And so in the y component, F net in the y is going to be equal to positive the total tension minus Fg1 minus Fg2 minus Fg3. And we are applying the equilibrium condition, which tells us that the net force has to be equal to 0. Meaning then the total, so this is positive, the total tension has to be equal to Fg1 plus Fg2 plus Fg3, which is going to be G times M1 plus M2 plus M3, which is going to be G times 15 kilograms. That is what the total tension is equal to. Now, all of this was predicated on you correctly identifying the pivot point. If your pivot point was incorrectly understood, your R's are all going to change. So you're going to have the wrong torque expression. So you're going to calculate or miscalculate what your mass is going to be, which is obviously going to throw off your overall tension numbers as well. So identifying the correct pivot point is absolutely crucial in these types of problems. Now here, there's only one additional topic we need to cover. We covered just angular motion, we covered torque, acceleration, rotational kinetic energy. What is the only thing we didn't cover? That's a complete different type of motion, but I'm talking about within rotation. What topic did we not cover? Is angular momentum. And we will call that L. Remember, angular momentum, momentum P is equal to mass times velocity. Meaning, when we apply this to rotation, L, the mass becomes the moment of inertia I, and V becomes omega. Now, just like how F, the force, turns into torque by doing R cross F, momentum, oh wait, why is that F net? Sorry, I meant this to simply be F. So momentum turns into angular momentum if we have the same R cross. So if it's a, so if we have an object spinning like this, remember the second right-hand rule? Your fingers goes in the direction of the curl. So take out your right hand. So if it's turning this way, this will be the direction of omega and angular momentum. In this case, let's say a particle was moving around in a circle. So let's say this was RV. And so then this would be our R vector. So momentum, remember, is mass times velocity, where mass is a constant. So ultimately, we're finding the cross product between r and the velocity. So r times r cross v. So our index finger goes with r, middle finger goes with v. Our thumb is pointing out. And so we would get the same understanding that this is going to be the direction of our angular momentum. Now this is important because L is conserved like P. L is conserved like P. And so this is one way to understand why bikes are more stable when you go faster. Why bikes are more stable when you go faster. So from a side view, there we go. There you go. All right, there we go. So when he's pedaling, right, that would be where the pedals are. The wheels are both going in this direction. Now let's say we're looking from the back. Okay? So we're going to look from the back. This is where the wheels are going to be. This is the person. There you go. You guys kind of see what I'm We're looking at his back. The wheels are turning this way. So which direction will the angular momentum be? So we take our fingers and it goes towards the curl of the wheel, and our thumb is actually our angular momentum velocity, or angular momentum vector. So the wheels generate an angular momentum in this direction. So the wheels are going like this, angular momentum is going to come out here. The faster you're spinning, the larger your angular momentum vector is. Meaning it's trying to keep it parallel to the ground. Parallel to the ground. This is why you are less prone to wobble, because as soon as you begin to wobble, what happens to the angular velocity vector? If you wobble like this, you are no longer parallel to the ground. So the fact that you're by your wheel spinning, it's trying to keep it upright and parallel to the ground, so it's going to correctly offset it. Or if you tilt the other way, your angular velocity looks like this, and so it's going to be corrected like the following. It's because when you're rotating your wheels, the angular momentum is this direction. It's trying to keep it parallel to the ground. Well, that concludes everything that we're going to be covering. On Wednesday, I will be going over the solutions to the quizzes, and there will be a short lecture on, remember, fluid mechanics, so that I can actually, and we'll cover that in a quiz, but it won't actually make it on the final. It will just be on the quiz, not on the final.